To consider the optimal placement for a technologically advanced civilization within the vastness of a galaxy, one must first dismantle our anthropocentric biases regarding planetary habitability and look toward the extreme physics of relativistic environments. We begin our analysis at the heart of the stellar system. The premise, often discussed in theoretical xenology and astrophysics, suggests that as a civilization matures, overcoming the initial hurdles of energy scarcity and interstellar travel, its primary currency shifts from material resources to information. The accumulation of knowledge requires time, vast stretches of it, to observe the slow evolution of the cosmos. However, biological or even post-biological entities are bound by the entropy of their own local frames of reference. This brings us to the counterintuitive yet physically robust conclusion that the most advantageous real estate in the Milky Way, or indeed any spiral galaxy, is not the quiet, spiral arms where humanity currently resides, but the chaotic, high-energy environment of the Galactic Center. The specific target for such a migration is the immediate vicinity of a supermassive black hole. In our galaxy, this corresponds to the radio source known as Sagittarius A. The reasoning relies heavily on the predictions of general relativity, specifically the phenomenon of gravitational time dilation. To understand this, we must visualize the fabric of spacetime not as a static stage, but as a dynamic manifold that curves in the presence of mass energy. A supermassive black hole represents a region of infinite curvature at the singularity, but even at a safe distance outside the event horizon, the boundary of no return, the gravitational potential is immense. According to the Schwarzschild metric, which describes the geometry of spacetime around a non-rotating spherical mass, the passage of time is inextricably linked to one's proximity to the gravitational source. For an observer situated far from the black hole, let us call this the observer at infinity. A standard approximation in physics, time flows at a standard rate. However, for an observer deep within the gravitational well, hovering just above the event horizon, time slows down significantly relative to the outside universe. This is not a biological illusion or a mechanical failure of clocks. It is a fundamental dilation of the temporal dimension itself. A civilization capable of engineering starships that can withstand the radiation environment of the galactic core could park their habitats in a stable orbit near the Schwarzschild radius. In this region, a period of mere days or weeks for the inhabitants might correspond to decades, centuries, or even millennia passing in the external galaxy. The strategic utility of this relativistic time compression cannot be overstated. By residing in this slow time zone, a civilization effectively hits the fast-forward button on the rest of the universe. They could dispatch automated probes or crewed vessels to explore the spiral arms, catalog star systems, and observe the rise and fall of other species. These probes, traveling at sublight speeds, would require tens of thousands of years to traverse the galactic disk. To a stationary observer on Earth, the wait for the probe's return would be excruciatingly long, effectively exceeding the lifespan of any coherent political entity. However, for the central civilization, the mission duration would be compressed into a manageable time frame. They send out a fleet, wait what feels like a few years, and the fleet returns with data gathered over immense epochal spans. They become the ultimate archivists of cosmic history, living in a relative stasis while the universe furiously evolves around them, delivering information to their doorstep at an accelerated rate relative to their subjective experience. This theoretical maneuver prompts the immediate question of physical survivability. The environment near a black hole is traditionally depicted as a realm of absolute destruction, a reputation that is partially deserved but nuanced by the scale of the object in question. We must distinguish between stellar mass black holes, the remnants of massive stars, and the supermassive giants that anchor galaxies. The danger posed by a black hole is often quantified by the tidal forces it exerts. Tidal force is the difference in gravitational attraction acting on the near side of an object versus the far side. If a human astronaut were to approach a stellar mass black hole, perhaps 10 times the mass of our Sun, the Schwarzschild radius would be roughly 30 kilometers. At this proximity, the gradient of the gravitational field is incredibly steep. The pull on the astronaut's feet would be significantly stronger than the pull on their head, overcoming the molecular bonds holding the body together. This process, vividly termed spaghettification, results in the object being stretched vertically and compressed horizontally into a stream of subatomic particles long before crossing the event horizon. However, the physics paradoxically favors the giant. The radius of a black hole scales linearly with its mass, but the tidal force at the event horizon scales inversely with the square of the mass. This means that as a black hole grows more massive, its event horizon expands, pushing the point of no return further away from the central singularity, where the mass is concentrated. For a supermassive black hole with a mass of millions or billions of solar masses, the event horizon is located at such a great distance from the singularity that the gravitational gradient across a human body, or a starship, is negligible at the crossing point. One could theoretically cross the event horizon of a supermassive black hole without feeling any local physical distress. The tidal forces would not be strong enough to disrupt biological structures or mechanical integrity. Therefore, the central galactic civilization could operate surprisingly close to the horizon, or even theoretically inside a very large one, without being ripped apart, provided they can manage the radiation from the accretion disk, the swirling maelstrom of matter falling in. This concept of settling near the abyss leads us to consider the broader dynamical context of our galaxy. We are not merely rotating in isolation. The Milky Way itself is being acted upon by vast external gravitational forces. When astronomers began mapping the velocity fields of galaxies in our local universe, subtracting the general expansion of the universe known as the Hubble flow, they detected a peculiar motion. The universe is expanding, and generally, galaxies recede from one another. However, this expansion is not perfectly uniform because matter is not distributed perfectly evenly. Regions of higher density exert a gravitational attraction that counteracts the expansion. We have observed that the Milky Way, along with the entire local group of galaxies, including Andromeda and the Triangulum Galaxy, is streaming through space at a velocity of approximately 600 kilometers per second toward a specific region in the southern sky, located in the constellations of Hydra and Centaurus. This motion indicates the presence of a colossal gravitational anomaly, a concentration of mass so immense that it dominates the flow of matter across hundreds of millions of light years. This structure has been designated the Great Attractor. The Great Attractor is not a single object, but rather a gravitational focal point, likely a massive supercluster of galaxies. Its precise nature remained elusive for decades due to a frustrating cosmic coincidence. It lies almost exactly behind the zone of avoidance. The zone of avoidance is the plane of our own Milky Way galaxy, which is thick with interstellar dust and gas. This material absorbs visible light, effectively creating a blind spot in our map of the external universe. We are trying to look out at the distant universe, but our view is blocked by the stars and nebulae of our own galactic home. It is akin to trying to see a distant mountain while standing in a dense forest. Only through the use of X-ray and radio astronomy, wavelengths that can penetrate the galactic dust, have we begun to peer through this veil. We now understand that the great attractor is a mass concentration equivalent to tens of thousands of galaxies, pulling our local sector of the universe toward it. It acts as a gravitational basin, a valley in the topology of the cosmos into which we are slowly sliding. However, the narrative of the great attractor is complicated by the discovery of an even larger structure beyond it. The great attractor itself appears to be moving toward an even more massive concentration known as the Shapley supercluster. This nesting of structures, galaxies flowing toward clusters, clusters flowing toward superclusters, reveals the hierarchical nature of the cosmic web. We are part of a river of galaxies, the Laniakea supercluster, flowing toward a density peak that we will likely never reach. The accelerating expansion of the universe, driven by dark energy, ensures that the space between us and these distant attractors is stretching faster than we can traverse it. We are running a race against the expansion of space itself, a race we are destined to lose, leaving us isolated in our local patch of the universe in the distant future. This discussion of flow and boundaries brings us to the ultimate question of cosmology. Does the universe itself have a boundary? When we speak of the edge of the universe, we must be precise in our definitions. There is a fundamental distinction between the observable universe and the global universe. The observable universe is strictly finite. It is a sphere centered on the observer, with a radius determined by the distance light has been able to travel since the Big Bang, approximately 13.8 billion years ago. Because the universe has expanded during this light's journey, the sources of that light are now roughly 46 billion light-years away. This particle horizon constitutes a hard physical limit to our knowledge. Beyond this sphere, there are undoubtedly more galaxies, more stars, and more space, but their light has not yet had time to reach us. They are causally disconnected from us. Regarding the global universe, the totality of all that exists, modern cosmological models, supported by measurements of the cosmic microwave background radiation, suggest that space is spatially flat to within a very small margin of error. In a flat universe, Euclidean geometry holds true on large scales. Parallel lines do not meet, and triangles have angles summing to 180 degrees. Crucially, a flat universe is generally understood to be infinite in extent. It does not curve back on itself like a sphere, nor does it possess a physical edge. A boundary would imply something outside, which contradicts the definition of the universe as containing all physical existence. If the universe is indeed infinite, the implications are staggering and move from the realm of astrophysics into statistical probability. In an infinite universe with a finite particle arrangement, repetition is inevitable. Matter can only be arranged in a finite number of quantum configurations within a given volume. If you have an infinite number of volumes to fill, eventually the arrangements of particles must repeat. This leads to the mathematically sound, albeit existential, conclusion that if the universe is truly infinite, there are regions of space far beyond our observable horizon that are identical to our own. There is a copy of our galaxy, a copy of our solar system, and indeed a copy of you, reading this text at this very moment. This is not a parallel dimension or a multiverse theory in the quantum many-world sense. It is a simple consequence of ergodic theory in an infinite spatial volume. The distance to such a doppelganger is calculably immense, a number so large it requires double exponential notation to express. But in an infinite expanse, it is statistically certain to exist. We must also address the exotic solutions to the Einstein field equations that allow for connectivity between these distant regions, the wormholes. In the context of general relativity, a wormhole, or Einstein-Rosen bridge, is a topological feature of spacetime that would essentially be a shortcut through a higher dimension. Imagine the universe as a two-dimensional sheet of paper. To travel from point A to point B requires traversing the surface. If one were to fold the paper and punch a hole through the touching layers, the distance becomes zero. This is the geometric function of a wormhole. While theoretically permitted by the math of relativity, the physical realization of a wormhole requires a substance known as exotic matter, matter with negative energy density, to stabilize the throat of the tunnel. Without this negative energy to push the walls apart, the wormhole would collapse under its own gravity the instant a single photon attempted to pass through. If such structures could be stabilized, they would offer more than just spatial transport. They would act as time machines. By accelerating one mouth of a wormhole to relativistic speeds and then bringing it back, one could desynchronize the time between the two openings. Stepping through one end would deposit the traveler in the past or future of the other end. This potential creates causal paradoxes, such as the grandfather paradox, which many physicists believe suggests that the laws of the universe fundamentally prohibit the formation of stable macroscopic wormholes. Nature appears to abhor a paradox. In the taxonomy of relativistic objects, we must also consider the theoretical opposite of the black hole, the white hole. The equations of general relativity are time-symmetric. If you film a movie of a planet orbiting a star and play it backward, the physics still makes sense. Similarly, if one mathematically reverses the collapse of a black hole, one obtains a solution describing a white hole. While a black hole is a region of spacetime that nothing can escape, a white hole is a region that nothing can enter. It is a singularity that exclusively expels matter and light. In the past, white holes were considered purely mathematical artifacts with no physical counterpart. However, some modern theories of quantum gravity, such as loop quantum gravity, suggest that white holes might be the final stage in the life cycle of a black hole. When a black hole evaporates via Hawking radiation, it shrinks. The theory posits that when it reaches a microscopic, quantized size, the internal spacetime structure rebounds. The gravitational collapse halts and reverses due to quantum pressure, transforming the black hole into a white hole that explosively releases the information and matter locked inside. This process would happen almost instantly for the black hole itself, but due to the extreme time dilation we discussed earlier, the transformation would appear to take billions of years for an outside observer. It is even hypothesized by some cosmologists that the Big Bang itself may have been a white hole event, a singularity unfolding and expelling the spacetime and matter that constitutes our universe. This brings us to the life cycle of the universe itself. The current standard model, lambda CDM, describes a universe dominated by dark energy and cold dark matter. Dark energy acts as a form of anti-gravity, a repulsive pressure inherent to the vacuum of space that drives the accelerating expansion of the universe. This force is pushing galaxies apart and determining the ultimate fate of the cosmos. If dark energy remains constant, the universe will expand forever, cooling and darkening in a big freeze or heat death. However, alternative models exist. If the density of the universe were higher, or if dark energy behaves differently over time, the expansion could eventually halt and reverse. Gravity would overcome the expansion, pulling all galaxies back together. The universe would shrink, heat up, and densify, culminating in a big crunch, essentially the Big Bang in reverse. This scenario opens the door to cyclic cosmologies. In a cyclic model, the Big Crunch is not the end, but the precursor to a Big Bounce. The universe creates a singularity, bounces, and expands again in a new Big Bang, initiating a new aeon of existence. Roger Penrose, the Nobel laureate, proposed the conformal cyclic cosmology, which suggests that in the unimaginably distant future, when all stars have burned out and all black holes have evaporated, the universe will contain only photons and thermal radiation. In such a universe, mass ceases to exist. Without mass, there is no scale or clock. Particles traveling at the speed of light do not experience time or distance. In this conformal geometry, the infinitely expanded, cold future of one aeon becomes mathematically identical to the incredibly hot, dense beginning of the next Big Bang. It suggests that our Big Bang was merely the conformal evaporation of a previous universe, and our future is the seed of the next. Thus, we see that modern cosmology paints a picture of a universe that is far stranger than our intuition allows. It is a place where time is a variable geography, where gravity can sculpt shortcuts through the void, where the edge is merely a horizon of information, and where the end may simply be a transition to a new beginning. We are observers trapped in a local frame, attempting to deduce the geometry of the infinite from our small, spiraling vantage point, pulled by attractors we cannot see, toward a future we can only calculate, not experience.